Hi. Today we are going to talk about displacements, displacement gradients, and string. So what we want to do is to describe how bodies deform. For that, we need to find a way to label the particles in the body, and the starting location is the label for the particles. Right? We need to assign such a way that each particle has a unique label. So what it is that we have to pick some shape for the object so that we can label it and use this particular location as a label. Here I have shown a rectangular object and it is in a particular shape. You can pick any convenient starting location. The simplest is to pick what is called its natural configuration. The location of the body when there are no forces on it are the easiest way to pick. So starting configurations, if you want to describe it mathematically, you have to put some inequality. In this particular case, it is x going from one to the other, y going from some of one value to the other. So that's how you have to describe a rectangle. To do this, you have to start by drawing the blob. And then you have to choose the axis and the origin and put 0, 0 there. And then you have to pick units and mark the points, and then you can write inequalities to represent the object. Okay, this is the starting point. Once you have done that, then you can label every particle with its location in this configuration. So this is our reference. This is our list. Okay, so this is how we start. Okay, now I want to describe the motion of a body. So the way we do that is by describing a displacement function, which is u of x comma t. Okay, vector u, vector x. For example, I have one which says u of x comma t in 2 dimensions is 3x squared plus 2y squared times t over 4, 3y times 1 minus cos 3t. Okay, this is my function u of t. Once you have picked it, you can now describe the motion. How do you do that? At time t equal to 0, we are at the starting point capital X. After that, its current location is reference location plus displacement vector, which is x plus 3x squared plus 2y squared times t over 4, y plus 3y times 1 minus cos 3t, or so that's how we specify the current location. We can plot it by picking a large number of points and see what shape you will get out of this large number of points, which is what I'm going to do now. So there, I picked this particular function, and I picked a large number of points like a point cloud, and I showed you what happens. So you will see that it changes the shape of the body in some complicated way. Point clouds are very convenient for certain purposes, especially for things which are called digital image correlation. This is how they find out how bodies move, by spraying particles all over and tracking them. In fact, you have seen that with CGI movies and all of that. That's how they do it. There's another way to do it, which is by drawing a grid. So with a grid, it's easier to see the motion, and we will actually use this much more than the point cloud technique for our class. Okay, but sometimes point clouds are convenient. So this is how we describe motion. Okay, the displacements describe both change of shape and orientation of the body. Okay, can describe any motion you like. If the motion is such that it preserves the distances between any 2 points in the body, then it is called a rigid body motion. Okay, for example, if you pick your displacement vector, if displacement function as cos t minus sin t, so cos tx minus sin ty minus x, and sin tx plus cos ty minus y, then you will see that it represents a rotation going round and round like that. You can see that the triangle mark there does not change its shape at all, because no lengths are changed. On the other hand, motions that do not preserve distances are called deformations. So here you can see that the triangle actually changes shape as this thing deforms. In fact, the takeaway message for this is that for motion to be a deformation, all you need is at least one triangular patch that changes distances between points. Okay, so there you go. That's a rigid body motion. You can see that. So how do we do this in a systematic way? Shape functions are a way to simulate shape changes in patches. So I'm going to pick a particular one. We start with a square body like that. And we are going to consider a displacement function, which is very simple. U, which is a vector, is a1, which is a vector, plus a2 times x, plus a3 times y. a1, a2, a3 are vectors, x and y are scalars. I got a vector function, right? Notice it is linear. So the first question for you to think about is, what is the meaning of the three vector coefficients AI? What do they mean? So I want you to pause this lecture here and think about it for yourself and try and see what they might mean. Did you pause? Did you think about it? Okay, I will show you what I meant. So if you look at the location, what happens to the point 0, 0? It will displace by a1. You can put x equal to 0, y equal to 0. So you can see the displacement of that point is a1. So that's the meaning of a1, displacement of the origin. Meaning of a2 is somewhat complicated. Relative displacement of the corner with respect to the origin. You can see the total displacement is a1 plus a2. Third one is a1 plus a2 plus a1 plus a3, like that. And that's it. Those three corners are prescribed. Okay, now let's see what will happen if I just have a2 plus a2 and a3 equal to 0. So u is just a constant, a1. What do you think will happen? So think about it. Pause the video, think about it, and then continue. Did you think about it? Did you pause? This is what happens. Okay, so I start out with a rectangular blob. Every point is moving by the same distance, a1. So what will happen is the whole body will translate. So a1 represents pure translation of the body. What shape will I get if all three are non-zero? If a2, a1, a2, a3 are non-zero, you can see that things can spread around depending upon where the two corners go. So I'll show you what will happen for a particular choice. You can see that it slowly deforms and it will become a parallelogram. Can you see? Okay. The question to you is, can we make the square become a quadrilateral or some other shape with just this function, a1 plus a2x plus a3y? If not, why don't you think so? If you think so, can you make it happen? Okay. If actually you cannot, because all the other points are determined only by a1, a2, a3. Once these 3 points are fixed, everything else is fixed. You can only generate parallelograms out of this, or triangle. You can make any shape for a triangle, but you cannot make any shape for a rectangle. It can only be a parallelogram. So this is a very limited shape. This is called a linear shape function. Okay. Now, can we generally try different things? The answer is yes. Right. So see that again. See how it goes. Now, we can try any other polynomials. Usually we can write, actually this is a simple thing. We can always write any polynomial vector function as scalar polynomials with vector coefficients. So we are now going to try something different. Again, we're going to start with the same square. This time I'm going to try something that is 4 terms. a1, a2, a3, a4 can be any vector you like. X, y, and xy are the functions. So first of all, it's not linear because it is multiplied. The inputs are multiplied. But in each variable, it's linear. This matters. This particular thing is called a bilinear one. And by the way, in finite elements, this is the workhorse shape. This is what all finite elements will use for doing two-dimensional problems because they are very convenient. Okay. Now let us look at what happens. What is the meaning of A? Okay, so I will let you think about it. It again depends upon the 4 corners now, not just 3 corners. I want you to think about it and see. Okay, can we make the square become a trapezoid with this function? How about a quadrilateral? I will show you that it can make a quadrilateral. There you go. You can see the quadrilateral being formed. But you can see that inside the quadrilateral, it's not linear. The boundaries are all nice and straight, but inside it's not actually straight. Okay, you can kind of sense that it is somehow warped in some way. Okay, but we cannot bend it. Can you see? The edges are always straight. Can we bend the edges with this? The answer is no, because it is bilinear. It is linear in X, it's linear in Y. For you to be able to bend it, you need at least something that is quadratic or cubic or something else in one of the variables. So I'll show you, you can generalize this quite a lot by mixing different polynomials for ux. We can control whatever shape we want. If you choose cubic or higher, you'll get a sort of snake-like motion. Okay, if you pick u of x is a0 plus a1x plus a2y plus a3xy plus a4x squared plus a5x cubed plus a6x squared y plus a7x cubed y, whatever. Pick something, put a0, a1, a2 vectors, whatever you like, you'll get all kinds of shapes. You have lots of degrees of freedom. In fact, with a particular choice, you can see I can get a very strange motion. You can see the top is bent, the bottom is straight. I can get that. I can get very complicated motions out of changing these functions. Okay. By the way, writing the polynomial in terms of x, y, in terms of powers of x and y is not such a great idea because it will get more and more difficult to interpret a0, a1, a2, and all of these things. So you can rearrange the polynomial so that the AIs have specific meanings. And these rearranged polynomials have names, right? Depending upon what kind of meanings their coefficients have. So we are not going to explore that, but this is actually something that you can play around with and see. So for example, Lagrange polynomial is just a polynomial written in a way that is convenient for a particular way of interpreting. Hermite polynomials, Bezier polynomials, spline functions, all of them were invented to be able to simulate shapes. By the way, polynomials are not very expressive. They are not very flexible. So especially for CGI and other things, they're not super flexible. So what they do there is to use ratios of polynomials. And these ratios are called NURBs, non-uniform rational B-splines. There are other things which are called T-splines and all kinds of things. Very advanced stuff has been done just by trying to say what kind of polynomials to use. We are done in terms of describing how deformations can be represented by using displacement functions. And the use of polynomial displacement functions with vector coefficients allows us to map all kinds of shapes. And these are at the heart of shape functions in finite elements. Thank you.